If you turn to page 25, besides the notation craziness that happened with the first part, the lower and the upper also caused mathematicians some pain because sometimes the lower rectangle used the left side point. Sometimes the lower rectangle had to use the right side point, especially when we did that cosine one, right? It was increasing then decreasing, so which were your points? Got a little bit complicated. So the mathematician Riemann comes along and says, well, if, and this should be, is this, can we fix it with a capital S in yours?
Yeah.
Okay, good. If the area is equal to the limit of the lower sums, and that's equal to the limit of the upper sums, Riemann was like, this is complicated because we have to, like, if you're doing the work and you wanted to do a bunch of it, it gets complicated because sometimes it's the left side, sometimes it's the right side. Okay? So we also are going to list the following assumptions that have to happen for this to work. So again, just like our mean value theorem, intermediate value theorem, and extreme value theorem, we're imagining our function to be continuous on that closed interval. Up till now, we've only done area under a curve, because mathematically this is how it started, with things above the x-axis. So the function's not negative between a and b. And then we divided it into equal subintervals where the change in x was always the distance divided by how many subintervals you had. And the little c was the absolute minimum and the big C the absolute maximum. So Riemann's like, this gets a little bit complicated. Maybe there's a better way about going to this. So if you pick a random thing in each of the intervals. So in each of the intervals, Ci was the smallest one. Capital Ci is the biggest one. If you picked another random point in between those two, guaranteed that it would be in between those two. Does that make sense? If you've got your maximum and your minimum, you pick another point, it's going to be in between them. Okay? Since the change of x, here's all of our changes of x's. These are all of the rectangles. So this f of Ci is always the height of your rectangle. Change of x is always the width. So the smallest rectangle is going to be less than or equal to the biggest rectangle. And if you picked a random point in between, well, then that rectangle would have to be obviously in between those two. So all of the sums of those rectangles, therefore, this is the minimum, this is the maximum, has to be somewhere in between if you pick random points. And since the sum of all of those little ones and the sum of all those big ones, the one in the middle has to be in between. And if we went to infinity, we get the area if we use the little or the big one. So obviously if we use any point, we'll get the area as well. And this is what Riemann developed. He said, why are we wasting our time always trying to find the minimums, always trying to find the maximums? It really doesn't matter. He's going to go so far as like, you know, if you want to, you can make the sizes of your rectangles like randomly different sizes. As long as you go to infinity, it's not going to matter. But keeping them the same size is pretty mathematically usually the easiest thing to do. So he's like, oh, well, I can just use the squeeze theorem and this has to happen. And so Riemann says, well, instead of doing all that complicated, always trying to figure out which one's the smallest, which one's the biggest, we can just do left Riemann sums. Always use the left side. I don't care if it's above or below. Always use the right sides. I don't care if it's above or below. And maybe I just use all the midpoints. And whether I use a left Riemann sum, a right Riemann sum, or a midpoint sum, if I go to infinity, it will equal the same thing. But if I just use these partially, it will give me a good estimate. So for Riemann sums, we're still saying that the function is defined, aka it exists. He found out that it doesn't have to be continuous. Interesting. Okay, so we add on stuff, and it doesn't have to necessarily always be positive. And we don't have to make the widths necessarily equal. So he's breaking down some of the restrictions we had at the beginning. And you can pick any number and still get an area under the curve. So on the exam, these are more typical questions. It's very rare I've seen finding using only the lower points or the upper points, but they do like to ask questions with left Riemann sums, right Riemann sums, midpoint Riemann sums. So you've got a function here, x squared minus 3 from 0 to 6. They give you subintervals, which are not necessarily the same size. And we want to find the left Riemann sum. So for the left Riemann sum on each of the intervals, you'll be using the left point to determine the height. If it was a right Riemann sum, you would use the right point to determine the height. Now, the 4 here at the end, that's not the height. Okay? The height is what would happen when you plug 4 squared is 16 minus 3. This height here is 13. But we're using all of the left heights, and you can see that labeled here with the dark red lines. And the widths of the intervals are different. From 0 to 1, this width is 1, this width is 1. From 2 to 4, it's 2, and from 4 to 6, it's 2. We take our left points and plug them in to find our heights, and then we sum up all of these rectangles. In our sum notation, what am I doing here? I'm doing from 1 to 4. I'm plugging in my left values. So in this case, the UI is standing for all of our left values. Change in X. And I have a little I with that now because my change in X is changing depending on if I'm on the first interval, the second interval, the third interval, or the fourth interval. Okay? I would be perfectly fine with you guys going, this and this are complicated for me. I just want to go to this blue step here as my first step. Perfectly fine, right? If you want to avoid the notation headache, if you say, I understand what I need to do, I need to add up all these rectangles. For each of these rectangles, I need to do height times width, height times width, height times width, height times width. Once I add those all up, and some of them are negative, I get 23. So now we can say the area under the curve, our estimate is 23. And just like we saw in the Mr. Bean video, this area is considered under the curve, even though it's above the curve. Right? Because area under the curve technically means area between the curve and the x-axis. This doesn't roll off the tongue. Area between the curve. Doesn't even make a nice acronym. So. And then, of course, here, this would be the area under the curve in that part. And the stuff that is below the x-axis, we always consider those areas negative. Because as we saw in the Mr. Bean video, another way to think about areas under curves is that if the graph is the graph of a rate of change, then the area under that curve is an accumulation of the change that's happening. Find the mid Riemann sum. So now, you're going to be using the midpoint of each interval to find your height. This looks like a better estimate, doesn't it? Just comparatively, what I like about this estimate is some of it's above, some of it's below. Seems like we have less error altogether. The widths of each of our intervals are the same. We can find, again, I don't know if you need to write this. I think if you were doing this question, you'd probably go right to here. Okay? These values here, the 1, the 2, and the 2, those are the widths. And the -11/4, the -3/4, the 6, and the 22, that's what you get when you plug your midpoint into the function to find the heights. All right, I'm going to show you the stuff you don't need to write. Right? Save you their guilty conscience of I didn't write something down that was on the board. Are you okay with that? Again, the idea, we're adding up rectangles. Again, I think the idea itself is not very hard. The notation is probably the hardest part, to properly write notation, but if we can skip some of that, and these are typically multiple choice questions, right? So it's not like you're just going to be able to guess and see the right answer. You're going to need to know how to do it, but you're not going to get deducted for notation errors on multiple choice. So we just need to find, for rectangles, width times height. And the height you will always get from your equation, right? By plugging in the values. And this time the values we plug in are our midpoints. Okay. Do you have an A in yours? Did I fix that? Or is it still approximately R? Oh, you're gonna have to add an A. Or maybe R is just an approximation for area. It's not quite the area. It's the New English word for an approximation for area. That could be a nice mathematical way to further confuse students, right? Instead of having to write approximate the area, I just write R. And you know that that means area approximation from now on. Okay. So we've got -x² plus x plus 2. We've got a picture of it here. We want to go from 0 to 2 with 4 equal sub-intervals. So let's figure out what our change of x would be. From 2 to 0 is a length of 2. Dividing that into 4 equal sections would give you a half. If you wanted to, sometimes people write each interval. So I would go from 0 to a half to 1, 1 to a half. I'm sorry, 1 to 1.5, and then 1.5 to 2. Those are the intervals. Sometimes writing the intervals is nice because then instead of writing these left endpoints like this, I can just put an arrow to them. And it becomes obvious that those are the left side intervals. Okay, again, maybe I shouldn't have shown you this line. This line, I think you don't necessarily have to put, but you're going to plug in f of 0, f of a half, f of 1, f of 3 halves, get those values. And one of the things that you'll notice here, if your intervals are all the same, do you notice that I have half in all four of those terms. So instead of doing so much difficult mental math by timesing by half, I could factor that half out in front. That gives me a little bit easier mental math. I just now have to add the 2 plus the 2 plus the 2.25 plus the 1.25. And I'll end up getting 3.75. Look at the picture. Do you think this is overestimate or underestimate? Looks like I counted too much. Based on the shading of the rectangles, looks like there's more overestimate than underestimate. Okay. Write Riemann sum with 4 equal subintervals. So now we want to do the right side. Okay? You're going to get 2.75. I'll show this one. Save you some writing. Let's scroll down if you like to draw the picture. That one looks like an underestimate. I just asked myself is it dangerous as a math person? Sometimes you should and sometimes you shouldn't ask yourself mathematical questions because they end up causing you to think like, is there a possibility? So I'm looking at this and the question I have is, these are estimates, so they're not correct. Anytime that you have something, I guess there's a possibility by off chance it could be perfect, okay? But that would be very rare. Because of that, one of them is going to, each of them is either going to be an overestimate or an underestimate. My mathematical question is, could I come up with an example where the left and the right were both underestimates? Or is it that they would always, one will be, if one is an underestimate, would the other one be an overestimate? Using the same subintervals. My gut feeling is I can't think of an example where if one is an underestimate, the other one would also be an underestimate. I think that would be tough to do. But maybe no. I think one has to be an overestimate, one has to be an underestimate. So it sort of makes me feel like, well, if I took the average of these two, would I get a much better, if I did the left and I did the right and then I found the average, would that not be better? Okay. So next we're going to do the midpoints. Ooh, I like the midpoints here because for every rectangle it'll have some overestimate and some underestimate. That's kind of nice. What do our midpoints come to? Okay, 3.375. I'll go back. Is that enough work you want to show? Do you want to show some more? You want one more line? So what we're doing now, these are our midpoints that we plug in. Each of them times by half again. Everybody good? Here is a very typical AP style of question. They don't give you enough information. They just give you a table of values. We're told that a function is continuous on the closed interval from 0 to 12. And we have those tables shown above. What's the area under the curve from 0 to 12? It looks like we have not enough information, but we can use, and we're going to use the midpoint Riemann sums with 4 subintervals of equal length to approximate this. Here are our intervals: 0 to 3, 3 to 6, 6 to 9, and 9 to 12. Does that make sense that if your distance was 12 and you divided by 4, that your change of x would have to be 3? So each of those intervals of equal length would go from 0 to 3. The midpoints of each of these are 1.5, 4.5, 7.5, and 10.5. Isn't it nice that those values are on our chart? Can you visualize these rectangles? The first rectangle would have a width of 3. The height of that first rectangle is 1.45. Because if you plug 1.5 into the function, you get your y value is 1.45. Our second rectangle, again, a width of 3. What's its height? 5.05. Third one has a height of 12.25. And the fourth one has a height of 23.05. We can factor out the 3. We can put in all of those heights, add them up and multiply by 3. And we get an estimate of 125.4. So if this was a question on your AP exam and multiple choice, just a little bit of an analysis of this question. You need to know what a Riemann sum is. If you have no idea when you get into your exam what a Riemann sum is, you're going to be guessing. There's going to be no work you can do whatsoever, right? So we have to know that Riemann sums add up rectangles. There's 3 types: left, midpoint, and right Riemann sums. You have to know how to find your intervals. So there's going to be information. This one, they're equal. Sometimes they'll tell you the intervals. So you need to know your intervals will tell you the width of your rectangles. The left, the right, or the midpoint will tell you how to find the height. The height of your rectangle is your y value. Sometimes you have an equation, so you have to plug in something to find your y value. And sometimes you have a table of values, and here our y values are all given. Now, what we're going through is sort of the mathematical struggle of which is the best estimate we can come up with. We started with lower and upper and said, well, if you find both of those, it's going to be somewhere in between, right? But we ran into problems because the lower is like, it's tedious to find out. You have to like, oh, which is the lower one? Which is the upper one? So then Riemann comes along and says, don't worry about lower and upper. It's a pretty good estimate just to do left or right or the midpoint. And that makes our decisions less troublesome to figure out. And then, of course, someone comes along and says, well, if left, right, and midpoint is a little bit tricky, why don't we do trapezoids? Because everybody loves this formula for trapezoids. In fact, sorry, I'm going to get excited about math for a little bit. The trapezoid formula is like a very powerful formula. Because the trapezoid formula is actually the formula for rectangles. And actually the formula for triangles. And the formula, of course, for trapezoids. Because a rectangle and a triangle are actually special trapezoids. So I'm going to get a little off topic here and just talk about how the trapezoid formula works. Okay? Trapezoid formula here is 1/2 base 1 plus base 2 divided by height. Okay? So the idea of this is that here's base 1. If I added that to base 2, that's obviously too much. Okay? And if I do base 1 times base 2, and I draw a nice new rectangle with all of that, without the half there, that's too much. Okay? This base 1 that I drew here, if I just make a rectangle with that part, can you see that that's equal to this rectangle right there? And with the triangles, those two parts would be the same. And those two parts would be the same. And so when we do base 1 plus base 2 and make a rectangle with that with the height, we end up getting double of what we started with. Okay? This is true, obviously, with triangles. Here, I'll do a right angle triangle. Can you see that right angle triangle is exactly half of the rectangle? That's why our triangle formula is 1/2 base times height. Can you see you could use the trapezoid formula? Because in a triangle, what's the base at the top? 0. So this is 1/2 base times height with the triangle formula. And with a rectangle or a square, your base 1 and your base 2 are exactly the same. So it would be like, let's find out the area of 2 rectangles, and we can find out the area of 1 rectangle by just dividing by 2. What a brilliant idea. Let's just do extra work. So because the trapezoid formula is extra work for both rectangles and triangles, nobody ever tells you, hey, just remember the trapezoid formula and you never have to remember rectangles or triangles ever again, right? Another helpful thing for me, right? New Year's resolution, no area of a triangle formula. I can now use this. I should have thought of that yesterday when we did all those stupid little rectangles, right? That would have been so much better. Okay. So here is our trapezoid. What is a trapezoid? It is a 4-sided shape with 2 sides that are parallel. And what we're going to do is we're going to make, so this would be base 1, this is base 2, this is a trapezoid because this side, here sometimes we use arrows like that to show parallel. That's a trapezoid. It's turned upright though. Usually the turns, so the base 1 and base 2 are up and down. Now my base 1 and base 2 are on the side, right? But if you look at it like this, it could be fine. Okay? And if we use trapezoids, mathematicians are like, well, for the most of the time, these are really good estimates, right? These are great estimates. Don't look here, please. These are great estimates all the way through. But we still could possibly have some problem areas, right? But if you made your subintervals smaller, right, you will always get bad estimates when your subintervals are wider. the more narrow you get. As soon as I split this one in half, I'm like, oh my goodness, I've got really good. So this idea of using trapezoids could make things better. And the trapezoid sum is just the average of the left and the right. Because if you're using the left, you would get this rectangle. If you're using the right, you would get this rectangle. And cutting that with a trapezoid perfectly in half makes a triangle, which would be perfectly in half of that. So now we have two ways we can find the trapezoid sum. We can either use the trapezoid formula all the way through, which isn't too bad actually, or we could find the left one and the right one separately and find the average. Okay, this question is going to start to introduce you to some notation that we haven't formally learned yet. We are going to learn that this symbol right here, I'm going to highlight it, gives us the definite integral. And the definite integral wants to find the area, quotation marks, under the curve, right? Because sometimes it's above, sometimes it's below, but between the curve and the x-axis, but we'll still say under the curve. This is going to find the area under the curve, starting at 1 and going to 2. And we're going to use 4 sub-intervals. So what are our intervals? Right? If you go from 1 to 2, that distance is 1 divided by 4. That means, I probably have it written right here. Our change of x is 1 over 4. For me personally, I do like to find, to do your left sums. Oops, oh no. There we go. To do your left sums, you'd have to find all of your left points. F of 1, F of 5/4, F of 3, F of 3 halves, and F of 7/4. To find your right sums, you'll need to plug in all of your right values. I'm going to show you some cool stuff on your calculator that can make finding these answers quicker. Okay? So I'm going to get this 0.6102 and this 0.7069 and show you some calculator tricks to do that. So first of all, our equation is sine x over x. I'm going to go to y equals. I'm going to make sure everything we do with integrals and derivatives needs to be in radians. I'm going to make sure that I'm in radians. I'm going to go to y equals and write sine x over x in my equation. I'm going to show you a couple of things that can be helpful with a graphing calculator here. So what do we want? We're going to need to figure out what sine of 1 is, sine of 5/4, sine of 3/2, sine of 7/4. You can feel free, you could type this in, right? And then you're going to divide by x. So I already multiplied by the reciprocal, but you could type in sine of 5/4 divided by 5/4. But that's a lot of things to type in. I want to show you how you can get those answers quicker. Okay? The quickest way to start with, because why? I'll just start you with the quickest and then show you some other stuff after, or should I show you other stuff first? Because then you stay intrigued to the, I don't know. We'll see. I'll show you the quickest way first. So on my calculator here, I've got that set into y1. I want to figure out, and I've already factored out my 1/4. I'm going to put brackets. And then if I look at what each of these things are, right? This is f of 1, because I factored out the 1/4 already. This is f of 1 plus f of 5/4 plus f of 3/2 plus f of 7/4. You can write function notation in your graphing calculator. It's really cool. But we don't have f. What's the function that we used? It was y1. Okay? If you have the function menus across the top, I think it's f4. Yes. f4 gives you your y's. So I can do y1 of, put brackets, y1 of 1 plus y1 of 5/4 plus. Now, if you don't have the alpha f1, f2, f3, f4, because some of you don't, you can also find your y1 under variables here. Variables, which variables do we want? We want our y variables, we want our function. So a little bit more buttons to get to the y1. Next one was 3/2 or 6/4. I like using 6/4 because then, and 7/4. So I just typed in function notation of this instead of having to type in everything for it because I plugged it into y1. Push enter and I get the 0.707. All right, always a little bit of nervous stuff, right? Here's a shortcut on your calculator and it doesn't come up right. So that can be very nice that way. But let's say you were supposed to actually write down these numbers. You wanted f of 1, you wanted f of 5/4, you wanted f of 3/2, and you wanted f of 7/4. You wanted those values and you were supposed to fill it in a table and write them down. So another thing that's really helpful on your calculator is that your calculator has a table of values. And that's right above the graph button, it says table. So if I go to my table of values, I'm like, oh, this is handy. It's got 0, it's got 1, so I got 1, but I don't have 1.25. And I don't have 1.5 and 1.75. I wanted to go up by 1/4. There's two ways you can change it. You can, above the window button, it has table set. And if you go to that, you can set up all sorts of restrictions from your table. But the shortcut is, I want to start at 1. So I'm going to go to 1 and highlight it. And then hit your plus button. What do you want to go your change in your table? I want to go up by 0.25. If I push enter here, it starts at 1 and now is going up by 0.25. If I don't like that, I can just go plus 1 again. It goes back to 1, 2, 3, 4. Plus 0.25, right? Now I have these values. I could add this plus this plus this plus this together, right? And times it by 1/4. No, what was the number in front? Yeah, times by 1/4. And get my answer from those values. But typing in each of these numbers would be a little bit slower than what we did to begin with. But a table of values this way, you now can, like, I can go plus, oh, what if you wanted to go up by 1/3? Well, just write 1 divided by 3. Goes up by 1/3. Don't have to write 0.3 all the way through. What if you want to go up by, I don't know, sine of 2.8 radians. It'll do that. I don't know why we'd want to do that, but maybe we would like Riemann sums with widths of sine of 2.8, just to see if you have calculator skills. Yes.
What if you go up by a negative number?
Ooh, is it bother? I'm really excited about this. Step back in case the smartboard explodes. It goes down. Crazy. What if you went up by a formula? This I think it should struggle with. Oh, I can't use unreal results. I better quit. Still,
This isn't real mode. Is there an unreal mode?
there is. You go to the mode button and get a little bit unreal. Here's the real mode. You can scroll over here and get unreal and see what happens. Right? Real, Abby. This is unreal. And this is, Rioi. Very nice modes. Okay, we're going to stay in the real mode for now. And stay in English. But, yeah. You could just, have fun. Go unreal in German or something like that. Really push your limits. Okay, so some helpful things to see with your calculator. We could do the same thing left and right. We've got it now. Our trapezoid one will just be adding them up and divide by 2. Or you could have used your trapezoid formula. Is it all right if you don't write that down? Okay, I'll make some of you not feel guilty. I'm not even going to show you it, right? If you're bored on your own time, you can go, I'll put the notes on Teams if you really want them in there. But it's just the trapezoid formula 4 times. You'd have to use your left value and your right value and do the more complicated. So I guess if they're asking for the trapezoid sum, it's really an excuse to get you to do your left sum and your right sum separately. Okay, I'm gonna leave this one right now. We're gonna do the next one together. And then we're gonna end class with you trying page 32 on your own. I'll put up the answer so you can check it in the end. Okay? So here's another table of values. The following chart of velocities at different times estimate the displacement. So we're going to find out that, well, we've already found out that working backwards is an integral, right? Working forwards is a derivative. Working backwards is an interval. So in kinematics, right? If you start at velocity, if you integrate, you would get back to displacement. And now we're seeing that that integration is an accumulation of change. You can figure out area under a curve. And if that's working backwards, that's going to give us an estimate for our displacement. So the following chart of velocities at different times, we can estimate the displacement.
Sorry for the interruption. Any
Using
student
the
that's attending
trapezoid
the Wuthering Heights screening, please come down to the West Lobby immediately. Thank you.
All right, see you guys. Have a great weekend. Make sure that you've handed in your assignment. So notice that these from 1 to 3 has a width of 2, from 3 to 4 has a width of 1, from 4 to 8 has a width of 4, and from 8 to 9 has a width of 1. But Riemann's like, it doesn't matter if they're different sizes. We can still use it as an estimate. And our displacement is going to be the definite integral from 1 to 9 of our velocity with respect to time. There's our 4 intervals. So if we want to find the left ones, we take the width times the height, 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 and the height is plugging in the left side. And we can get f of 1, f of 3. I guess technically, if you haven't got here yet, change these to v's. We've got v of t in the question there. So v of 1, v of 3, v of 4, v of 8. And get those values. And we get. You just put them up. Your name's all there? Yeah. Excellent. We can get the left sides to be 27. Same thing, do the same process with the right sides. We get the right sides to be 15. So our trapezoidal sum will be 21. I just came up with a great example where if I use the left side, the right side, or the trapezoid side, they'll all be overestimates. So it's not like, I wondered, is one always an underestimate and then the other one always an overestimate? The answer is no. So I came up with this graph. I'm going to go from this point A to this point B, and so there's my A to B, and I'm going to do 2 subintervals. And do the rectangles for those 2 subintervals. This is my graph. Okay. So my left rectangle will use the left point. It would be this one. And use this left point. It would be this one. Obviously, that would be an overestimate. My right point would use this point, which would be this rectangle, and this point, which would be this rectangle. It is exactly the same as my left one. It's an it's an overestimate as well. And the trapezoid would be connecting these 2 points and drawing a line between them. Would be exactly the same a third time. And so I might get the assumption, I am amazing. My left, my right, and my trapezoid all equal. I must have found the area perfectly. No. All 3 of them in that example are overestimates. So our earlier question, because almost all of our examples had 1 be an underestimate, 1 an overestimate, and you're like, ooh, is my answer always going to be in between? No. Here's a fancy little sine curve. And if you choose the perfect intervals, you can screw yourself up. Really well. Okay, so try this last question on your own. For e to the x squared, I'll put up the answers in the end.